This is AQA A-Level Chemistry, part 6 of the energetics topic. So in the previous video, we looked at calculations where enthalpy of formation data had been provided. And we're going to round it up now by looking at what happens if enthalpy of combustion data is provided instead. And then overall, we're going to try and summarize key ways to navigate your way through either of those two types of calculation. It is worth pointing out that you are not guaranteed to be given enthalpy of formation or enthalpy of combustion. The vast majority of questions do follow that route, but more challenging ones can be given. And that's why it's really important that you have that knowledge and that confidence that underpins the actual building of Hess cycles that we spoke about in an earlier video in this topic. Okay, as always, I'm going to recommend that you have a go at each section. I'm going to pause and then review and double check that you're on the right track. So as I've said, we're looking at what happens when enthalpy of combustion data is provided. We've got a table here and we've got a question that we're going to build through very, very slowly. But similarly to how we did it with the enthalpy of formation, we're going to go through very much step by step. So have a think about these. And if you've had a go at writing them, let's take a look and see how we can apply our knowledge of the definition that we spoke about way back at the beginning of this topic. Enthalpy of combustion of, in this case, this is ethanol. We know that combustion will be a ready supply of oxygen, so it's going to be complete combustion. We know that we are going to have all reactants and products in their standard states at standard temperature and pressure, and we know that it's 1 mole of a substance being combusted. So when I look at this, I can see that when I combust, I'm going to get CO2 from the carbons and H2O from the hydrogens. And I still then need to balance it. So I've got 2 CO2 and 2 H2O, but actually I still need to balance the equation because the oxygens now are not correct in number. So I need 2.5 O2. Big thing to watch out for here. Remember, there's already an oxygen present. Don't just count up the 6 and go for 3O2. And then finally, we need the state symbols, and you will notice that the carbon dioxide is gaseous and the water is liquid. Even though when you combust ethanol, the water vapor would be given off, our enthalpy change value is what the change would be once everything has reverted to standard conditions. On the next one, combustion of H2 gaseous. Well, again, I react it with oxygen. When I combust, I make water. Remember, this is in the liquid phase. And then I simply need to balance it. So I need half an O2. And finally, enthalpy of combustion equation for the combustion of ethanol. Exactly the same process as we have seen. Going to make CO2 and H2O. I then need to balance it. So what we then need to do is start to build this into a cycle. And similarly to what we did with the enthalpy of formation equations, remember that the Hess cycle is a bit like a jigsaw. You've just got lots of equations slotted together, but they're not going horizontally left to right. So this is what we started with. This is the equation we're interested in finding the enthalpy change for. Now, if I combust CH3CH2OH, I make 2 CO2 and 3 H2O, which is exactly what I would make if I combusted an ethanol and a hydrogen. Now, you will notice the cycle here is not balanced for oxygens. You are welcome to balance for oxygens and put more of them in. It won't necessarily be credited with marks in the exam. So once I've done this, I can start to think about the calculation. So you can see here, I've brought the data forward again, my enthalpy of combustion of ethanol, hydrogen, and ethanol. And I've got my cycle there. So let's put the figures in. Well, my negative 1167 to combust an ethanol, my negative 286 to combust a hydrogen, and my negative 1367 to combust my ethanol. So if I then start to consolidate those figures, you can see that actually we've got a negative 1453 on this route and an X and a negative 1367 on the alternative route. Because as we did with enthalpy of formation, we've got to find what the two comparable routes are. And in this case, they both start on the top left and they end at the bottom. Once I've got that, I can start to put the figures into an expression. So x take away 1367 is equal to negative 1453. That then allows me to rearrange to make x the subject, taking me to a value of x of negative 86 kilojoules per mole. Okay, another one for you to try. And once again, what we do, we build our cycle. So 4C will give me 4CO2, 5H2 will give me 5H2O, and C4H10 will also give me the same product of combustion. At that point, I can substitute the figures in. Remember, I've got 4 carbons here and I've got 5 H2s, so I need to multiply the values accordingly. My C4H10, I have 1, so that's negative 2877. I can now build my expression. I've got my two roots. Again, they start at top left and go to the bottom, which will always be the root if enthalpy of combustion data is provided. There's my expression. Let's rearrange it to make x the subject, also expanding those brackets. And that takes us to an x value when I do the final simple calculation of negative 129 kilojoules per mole. Another one for you to try. And once again, we build the cycle. I have got 2C going to 2CO2, 3H2 going to 3H2O, and my ethanol will also give me those same products of combustion. You'll again note I have not balanced the oxygens on this. It's not required within the cycle. Now, once I've done that, I can put my figures in. Again, I've got multiple carbons, multiple hydrogens, so I multiply up the value. I find my two roots. I've got my red root and my green root here. And then I can substitute my figures into the expression. So x take away 1367 is equal to the sum of these. I can then make x the subject. And from there, I can work out the value of x is negative 279 kilojoules per mole. So we're going to finish off with a simple model that you can use. It's something that people will be familiar with, whether you follow a religion or not. But I'm going to use the concept of heaven and hell to try to remember some of the key facts and make this a little bit more manageable. Because if I take my AB equation and I think about in all of the enthalpy of formation calculations that I was given, which direction did the arrows go? Well, they pointed up as if to the sky, and it's like we're creating things from the elements that make them up. And if we think about the direction that the enthalpy of combustion calculations have gone, they point down. And again, if we're going to follow this analogy through, we can think of that pointing down to the product of combustion, to the fiery pits of hell. So a simple model, you might not need a model, but if you do, that could make it easier. That takes us to the end of this section. Thank you for listening. Goodbye.